okay, you've got plants, they need to respire, roots need oxygen. If you have organic matter, you tend to also get well oxygenated soils that are, organic matter improves just about all these things, soil structure, other kinds of things. Certainly organic matter, if you're looking at soil communities and all the creatures that are in the soil, the organic matter is kind of their main food and habitat. So it obviously has a big importance for soil biodiversity. So just the point about this was, apart from, again, if we're thinking back to the sustainability, yeah, the carbon balance is important for the CO2, but the soil organic matter status is also very important for kind of ecosystem health and lots of other things that you might include in this kind of sustainability stuff. And so, for example, if you want to have a well-functioning, fertile soil, organic matter is really one of the most important things that you can do. Erosion control is another aspect of just maintaining the soil, in its place. So these are, some of the key objectives for maintaining, good quality soils. And we talked about, we've already talked quite a bit about this whole issue of the carbon as a potential CO2 sink or a source the other way. Now, part of the potential trade-off, I guess, and not so much for the systems that you guys are doing, but in the previous years where we were doing analysis of corn stover primarily as a feedstock. That was at least one of the options. And I think, I don't know, the group doing poplar is also potentially supposed to look at wheat straw. So there's kind of a trade-off, right? The biomass you produce, you want to take away and convert it to fuels. It's also, the source for the organic matter that maintains, maintains organic matter in soils. And so if you remove that corn stover, wheat straw, how's that going to impact the soil carbon? It may have negative effects on it, and we'll look at how you might analyze that. But likewise, also there's the issue about, okay, if I'm looking at conventional cropland or pastures or some other land use, and now I'm going to plant poplars or I'm going to put miscanthus in their switchgrass. Those kinds of changes in vegetation and land use can have a big effect, on the soil carbon balance and that balance between the biomass production, the fuels, and what you leave behind. So this is kind of the, crash course in modeling. So, part of what you're going to be doing is looking at your ecosystems and trying to make predictions and assessments about how is soil organic matter, how is soil carbon going to change, under your biofuel business. Okay. And you're not going to run out and do measurements there. We're going to model it. And this figure kind of depicts, right, in the simplest terms, what it is. You've got carbon dioxide coming through the plant. Some of that, particularly the roots or residues left behind, is what is the source of the carbon that's stored in the soil. And then, of course, the soil organic matter is continuing under attack by microorganisms and is used as for an energy source, and so you've got respiration and CO2 release. So it's this dynamic equilibrium. So if you want to model the change in carbon as a function of time, okay, you want to look at soil organic matter over time, this would be about probably as simple as you can depict it, right? So the change in soil carbon over time is going to be equal to the amount going in to this box here. We can just treat it, then it's a constant. So it's 2 tons per hectare per year. And the rate of loss via decomposition of the carbon that's in the soil. And typically this, loss process through decomposition is very often, can be considered as kind of a first order process, okay, at least as a first approximation. Okay, so we pretty well defined a system now. Let's take a look at that and get this modeling over in a hurry. Oh. Okay, so let's think about so what's going to what's going to affect the whether you're gaining or losing carbon is going to depend on what? It's going to depend on the rate of input and the rate of decay. So if I want to look at that system where it's not changing, that would be to say, how does the system look at steady state? Everybody understand the idea of steady state equilibrium? So what's the amount of carbon at steady state in my system? I want C is equal to steady state means the rate of change is equal to 0, right? So I equals K times C divided by K. Okay. So what's that look like? It's a pretty easy graph. And I have inputs here. Stocks. Get something like this, right? Slope is 1 over K. What's another term for 1 over K? What does that represent? The system's in steady state. It's the K rate. What's the mean residence time of carbon in the soil? So if, for example, you said that the organic matter decayed on average about 2% per year. Okay, so K was equal to 0.02. Mean residence time then would be 50 years. That's per year. So you would say an average carbon atom would be resident in the soil for 50 years, and then would be eventually expired. So you could see, at steady state, it would be simple to say, okay, if I have my system, and now I'm going to change from annual crops to grasses, and I know the grasses put in a lot more carbon into the soil, maybe you move this way. And, and so you could say, well, my carbon stocks, might move up that way if nothing changed with respect to, the rate of decay. But maybe my grasses do something to change the soil water balance, and so decomposition either speeds up or speeds down. And so, you might also be then changing the slope in some way. And that's a simple analysis to sort of look at it in steady state. Now, in theory, how long would you, if this was this first order differential equation like that, if you wanted to say, okay, I want to estimate my, my change in soil carbon for my 20-year period of time. And you wanted to use this as the basis of the analysis. So if you change I and you are going to increase soil carbon to a new steady state, when are you going to reach that steady state? it's actually, you know, you're going to asymptote. You know, the system, as you change it, it's going to be asymptotic to that new steady state, and you actually, you know, will never reach it until time goes to infinity. But you can come, you know, awfully close, and depending on the rate of, you know, depending on this parameter, you know, it'll take a shorter or longer time to approach that new steady state. So what you do, of course, then is, you know, we're not going to be doing steady state analysis. That can be a useful approach to kind of look, you know, kind of an overview of the system. But what you're going to be doing is, you know, using simulation models to, you know, to essentially solve, you know, solve this differential equation. Okay, like we have here. Now this one, you know, depending on how you define I, you could integrate that as a closed form solution, right? But typically, for matters that we'll see in a minute, for the kinds of models of soil organic matter that you're going to want to do, you know, you can't do those sort of closed form solutions, and so you use simulation and numerical integration. That's really kind of all it's about. And I think the engineering types probably do perhaps much more complex modeling than lowly ecologists, but anyway. So, let's see. Actually, I didn't notice that before. I should use that one. Okay, so we kind of went through that. And yeah, the bad news, I guess, is it's not that simple. So why isn't it? Okay, if you define an entity, so that state variable, or what I was calling soil carbon, C, that is, I'm defining that as having a homogeneous property, okay, given by that K constant, which says something about the decomposition rate of that. So it's saying if all the soil organic matter was homogeneous and behaved the same way, then we can have a very simple model like that and things would be very easy. It's not that way though. Soil organic matter is incredibly heterogeneous, and people have gone out, I don't know if anyone here has done this, but lots of people have, is you can take soil organic matter and you can, in different ways, kind of fractionate it or break it up, and you can find, you know, some material which is kind of yesterday's crop residues. You can also find soil organic matter that is literally thousands of years old that is still sitting in the soil. And part of the, you know, the science of people that study this is kind of, you know, a little bit of head scratching of how, given that environment of all these hungry microbes, how can that organic matter persist for as long as it does in some of it. So, but you've got a range of, you know, very recent to very old stuff. The chemical structures of a lot of the compounds you can't directly determine. We're getting better and better with different methodologies to look sort of in situ and see more about the structural chemistry of organic matter. But it's still quite difficult. And it's not the same if you're, you know, Alicia, other people working in biology, you know, you've got, you know what the structure of your DNA is, right? You can count sort of every atom in it, and you know all this stuff. Well, it's not the same. You know, we don't have the same kind of well understood, you know, repeating molecules, if you will, that you deal with in living systems. And then a lot of the organic matter in soil is intimately associated with soil mineral particles, and this is really crucial. That's probably the key part